Now we are focusing on instrumentation. The Spring Instrument module provides the class instrumentation support and class loader implementation to be used in a certain application service. The Spring Instrument Tomcat module contains Spring's instrumentation agent for Tomcat. As an example, we can consider this Maven segment. Here you can see the artifact ID, Spring-instrument. Spring instrumentation provides class instrumentation support and class loader implementation to be used in application servers. As an example too, we can consider a package org.springframework.instrument. As an example 3, we can consider class instrumentation saving agent, Java agent that saves the instrumentation interface from the JVM for later use. This is in the package org.springframework.instrument. Spring Framework ships with an agent, for example, instrumentation saving agent, which is packaged in the spring-instrument.jar. For example, and you can use this with the as the value of the dash Java agent argument with Java command. As an example 4, we are considering Spring configuration. Again, following example specify the reflective load time viewer. The class reflective load time viewer load time viewer which uses reflection to delegate to an underlying class loader with well-known transformation hooks. The underlying class loader is expected to support the following viewing methods as defined in the load time viewer interface: public void add transformer, Java lang instrument.class file transformer for registering given class file transformer on this class loader; public class loader get throwaway class loader for a method for obtaining a throwaway class loader for this class loader. Optional reflective load time viewer will fall back to a simple throwaway class loader if that method isn't available. Please note that these methods must reside in a class that is publicly accessible, although the class itself does not have to be visible to the application's class loader. If you use XML based configuration, you can specify fully qualified class name as a value of the viewer class attributes on the context colon class time viewer, load time viewer element. Again, the following example specify reflective time viewer. As an example 5, we are considering Tomcat load time weaving setup 5.0 plus. Here the class Tomcat instrumentable class loader, extension of Tomcat's default class loader which adds instrumentation to loaded classes without the need to use the VM wide agent. This is in the package org.streamframework.instrument.classloading.tomcat. Apache Tomcat's default class loader does not support class transformation but allows custom class loaders to be used. Spring offers the Tomcat's instrumentable class loader inside the org.springframework.instrument.classloading.tomcat package, which extend Tomcat's class loader, web app class loader, and allow JPA class transformer instances to enhance all class loaded by it. In short, JPA transformers will be applied only inside a specific web application which uses the Tomcat instrumentable class loader. In order to use custom class loader, copy Tomcat. Step 1, copy Spring Tomcat viewer.jar into $Catalina home /server/lib, where $Catalina underscore home represent the root of the Tomcat installation. Step 2, instruct Tomcat to use the custom class loader instead of default one by editing the web application context file. Tomcat 5.0.x and 5.5.x series supports several context locations. Server configuration file $Catalina underscore home /config/server.xml. The default context configuration $Catalina underscore home /config/context.html that affects all deployed web application and per web app configurations deploy on the server. $Catalina underscore home /config engine name /hostname /web app context.xml side or along with the web app your web app.var /meta info /context.xml. For efficiency, inside the web app configuration style is recommended since only applications which use JPA will use custom class loader. Note that versions prior to 5.20 contains a bug in the XML configuration parsing preventing usage of loader tag inside server.xml, no matter if a class loader is specified or not, be it the official or custom one. If you are using Tomcat 5.20 plus, you can use system class loader per parent to false to fix the problem. You can add additionally here the use system class loader as parent equal false. With Tomcat 6.0.x, copy the copy a Spring Tomcat weaver.jar into $Catalina underscore home /lib, where $Catalina underscore home represent the root of the Tomcat installation. Step 2, instruct Tomcat to use the custom class loader instead of the default one by editing the web application context file. Like here in Tomcat 6.0.x, similar to 5.0.x and or 5.x series support several context locations. Server configuration file $Catalina underscore home /config/server.xml. The default context configuration $Catalina underscore home config/context.xml that affects all deployed web application and per web configuration deployed on the server. $Catalina underscore home /config/ engine name /hostname my web context.xml side or along with the web app your web app.jar /meta-info /context.xml. For efficiency, inside the web app configuration style is recommended since the only application which use JPA will use custom loader. The last step required is on all Tomcat versions is to use the appropriate load viewer when configuring local container entity manager factory bean. Following example shows a typical bean definition for a local container entity manager factory bean. The class instrumentation load time viewer start the JVM specifying the Java agent to be used. For example, as follows: when Spring Instrument version .jar is a jar file containing the instrumentation saving agent class shipped with the Spring, and where version is the release version of the Spring framework. For example, 5.1.5 release. This is in the package org.springframework.instrument.classLoading. You can use when you are using local content entity manager factory bin, you can use this option for a full JPA capabilities in Spring based application environment. This include web containers such as Tomcat, standalone application integration test with sophisticated presence requirement. The local content entity manager factory bin gives a full control over entity manager factory configuration and is appropriate for environment where fine-grained customization is required. The local content entity manager factory bin creates a persistence unit info instance based on the persistence.xml file. The supplied data source lookup strategy and specified load time viewer. It is thus possible to work with the custom sources outside the JNDI and use to control the weaving process. The following example shows typical definition for local content entity manager factory bin. However, you can, if needed, manually specify dedicated viewer through the load time viewer property. As following example shows, the class reflective load time viewer. The load time viewer, which uses reflection to delegate to an underlying class loader with well-known transformation hooks. The underlying class loader is expected to support the following weaving method as defined in the load time viewer interface. Public void at transformer java.land.instrument.class file transformer for registering the given class file transformer on this class loader. Public class loader get throwaway class loader method for obtaining a throwaway class loader for this class loader optional. Reflective load time viewer will fall back to a simply throwaway class loader if that method isn't available. This is in the package org.springframework.instrument.classLoading. No matter how LTW is configured by using this technique, JPA application rely on instrumentation can run in the target platform, for example Tomcat, without needing an agent. This is especially important when the hosting applications rely on different JPA implementation, because JPA transformers are applied only at the class loader level and are thus isolated from each other. As an exception example, we can consider this here exception in main, etc. And here you can see a factory method public spring org.spring framework.instrument.class loading loading time viewer, and spring.org.spring framework.context, etc. And here the three exception. Nested exception is java.lang.illegal state exception class loader and does not provide an add transformer class file transformer method. Specify custom class load time viewer or start your Java virtual machine with Spring's agent dash Java agent or colon org.spring framework.instrument.java, etc. Now we are focusing on messaging. Spring Framework 4 include the Spring messaging module with key abstractions from the Spring integration project, such as message control, message handler, and others to serve as a foundation for messaging based applications. The module also includes a set of annotations for mapping messages to methods, similar to a Spring MVC annotation based programming model. The module also includes a set of annotation for mapping messages to methods, similar to the Spring MVC annotation based programming model. As an we can consider as an example, we can consider this Maven segment. Artifact ID Spring messaging. Spring messaging provides abstractions such as message channel, message handler, and others to serve as a foundation for messaging based applications. It also includes a set of annotations for mapping messages to methods. As an example too, we can consider package org.springframework.messaging, support for working with messaging APIs and protocols. Here as an example 3, we can consider this code segment. You can send a message to user destination from many application components by, for example, injecting simple message template created by the Java configuration, no XML namespace. The bean name is broker message template here if required for a qualification with at qualifier. The following example shows how to do it. The simple message template, the class simple message template, and implementation of a simple simp message sending operations. This is a simp messaging template. This is in the package org.springframework.messaging.simp. You can send a message to user destination from any application component. For example, injecting a simp messaging template like here. When you use user destination with an external message broker, you should check broker documentation on how to manage inactive queues, so that when the user section is over, all unique user queues are removed. For example, RabbitMQ creates auto delete queues when you use destinations such as /exchange/amq.direct/position-updates. So in that case, the client could subscribe to /user/exchange/amq.direct/position-updates. Similarly, ActiveMQ has configuration options for purging inactive destinations. In a multi-application server scenario, a user destination may remain unresolved because user is connected to a different server. As such cases, you can configure destination to a broadcast unresolved messages so that other servers can have a chance to try. This can be done through the user destination broadcast property of the message broker registry in Java configuration, and user destination broadcast attributes of message broker element in XML. Now we are considering token authentication in Stomp. The following example shows how to register custom authentication interceptor. Interface message. Generic message representation with headers and body. This in the package org.springframework.messaging. Note that the interceptor needs only to authenticate and set user header connect message. Spring notes and saves the authenticated user and associate it with subsequent Stomp messages on the same session. The following example shows how register a custom authentication interceptor. Also note that when you use Spring security authentication for messages, at present you need to ensure that the authentication channel interceptor config is ordered ahead of Spring securities. This is best done by declaring custom interceptor in its own implementation of WebSocket message broker configurer that is marked with at ordered dot highest precedence plus 99. Here you can see a WebSocket message broker configurer. Access authentication headers. As an example 5, we are considering create a message handler controller in WebSockets. For example, the greeting controller from, for example, here source main java.com example messaging Stomp WebSocket greeting control.java here, for example, is mapped to handle messages to /hello destination, as the following listing shows here. The annotation type message mapping. Annotation for mapping a message into a message handling method by matching the declared patterns to a destination extracted from the message. The annotation is supported at type level 2 as the way of declaring pattern prefix or prefixes across all methods. This is in the package org.springframework.messaging.handler.annotation. In Spring's approach to work with Stomp messaging, Stomp messages can be routed to at controller classes. For example, greeting controller is mapped to handle messages or to the /hello destination, as this following example shows. The controller is a concise and simple, but plenty is going on. We break it down to some steps here. The messaging at message mapping annotation ensures that if a message is sent to /hello the destination, the greeting method is called. The payload of the message is bound to a hello message object, which is passing into a greeting. Here simulated delay. As an example 6, we can consider class abstract message broker configuration provides an essential configuration for handling messages with simple messaging protocols such as Stomp. This is in the package org.springframework.messaging.simp.config. As an exception example, we can consider class messaging exception, the base exception for any failures related to messaging. This is in the package org.springframework.messaging. As an error example, we can consider this error. Reply message received, but the receiving thread has already received a reply message error message. Payload equals out.springframework.messaging.message handling exception. Now we are focusing on core container. The core container consists of the Spring core, Spring Beans, Spring Context, Spring Context Support, Spring Expression, Spring Expression Language modules. Now we are focusing on Beans. Spring Beans provides a configuration framework and basic functionality to instantiate, configure, and assemble Java objects. The Spring Core and Spring Beans modules provide the fundamental parts of the framework, including the IOC and dependency injection features. The Bean factory is sophisticated implementation of the factory pattern. It removes the need for programmatic singletons and allows you to decouple the configuration and specification of dependencies from actual program logic. Here you can see here's the steps involved in Spring Bean lifecycle. So this is Spring Bean lifecycle. find the Spring Bean lifecycle diagram here. Here showing the steps involved in Spring Bean lifecycle. A beam lifecycle includes following steps. Step 1, within IOC container, Spring Bean is created using class constructor. Step 2, now the dependency injection is performed using setter method. Step 3, once the dependency injection is completed, bean name aware.set bean name is called. It sets the name of the bean in a bean factory and that created this bean. Step 4, now code bean class loader aware.set bean class loader method is called that supplies the bean class loader to a bean instance. Step 5, now code bean factory aware.set bean factory method is called that provide the owing factory to a bean instance. Step 6, now IOC container calls bean post processor dot post process before initialization on the bean. Using this method, a wrapper can be applied on original bean. Step 7, now the method annotated with at post construct is called. Step 8, at post construct, the method initializing bean dot after properties set method is called. Step 9, now the method is specified by init method attribute of bean in XML is XML configuration is called. Step 10, and then bean post processor dot post process after initialization method is called. It can also be used to apply wrapper on original bean. Step 11, now the bean instance is ready to be used. Perform the task using the bean. Step 12, now when the application context shuts down such as by using register shutdown hook method, when the method annotated with at pre-destroy is called. After the disposable bean.destroy method is called on the bean, after that the disposable bean.destroy method is called on the bean. Step 14, now the method specified by destroy method attribute of the bean XML configuration is called. Step 15, before garbage collection, finalize method of object is called. Here void set bean name string name, set the name of the bean in the bean factory that created this bean. Void set bean class loader callback that supplies the bean class loader to a bean instance. Void set bean factory throws bean exceptions. Callback that supplies the owning factory to a bean instance. At nullable, default object post processor before initialization object bean string bean name. Apply this bean post processor to the given new bean instance before any bean initialization callbacks like initialization beans after properties set to a custom init method. Bean will already be populated with property values. The return bean instance may be a wrapper around the original. Annotation type post construct java.x annotation java.x.annotation. This is in the java x.annotation package. The post construct annotation is used on a method that needs to be executed after dependency injection is done to perform any initialization. This method must be invoked before the class is put into service. This annotation must be supported on all classes that support dependency injection. The method annotated with post construct must be invoked even if the class does not request any resources to be injected. Only one method can be annotated with this annotation. The method on which the post construct annotation is applied must fulfill all the following criteria. The method must not have any parameters except in the case of interceptors, in which case it takes an invocation context object as defined by the interceptor's specification. The method defined on an interceptor class must have one of the following signatures: void method invocation context, object method invocation context throws exception. Note: a post-construct interceptor method must not throw application exceptions, but it may be declared to throw checked exceptions, including the java.lang.exception if the same interceptor method interposes on business or timeout method in addition to lifecycle events. If the post-construct interceptor method returns a value, it is ignored by the container. The method defined on a non-interceptor class must have the following signature: void method open brace closing open bracket closing bracket. The method on which post-construct is applied may be public, protected, package private, or private. This method must not be static except for the application client. The method may be final. If the method throws an unchecked exception, the class must not be put into service except in the case of EJB, where EJB can handle exceptions and even recover from them. Void after properties set, invoked by the containing bean factory after it has set all bean properties and satisfies bean factory aware, application context aware, etc. At nullable default object post process after initialization object bean string bean name, apply this bean post processor to the given new bean instance after any bean initialization callbacks, like initializing beans after property set. This is the bean process after initialization method, or a custom init method. The bean will already be populated with property values. The return bean instance may be a wrapper around the original. The annotation type predestroy javax.annotation. This is in the package javax.annotation. The predestroy annotation is used on methods such as method as a callback notification to signal that instance is in the process of being removed by the container. The method annotation annotated with predestroy is typically used to release resources that has been holding. This annotation must be supported by all container managed objects that support post-construct except the application client container in Java EE5. The method on which the predestroy annotation is applied must fulfill all of these following criteria. The method must not have any parameters except in the case of interceptors, in which case it takes an invocation context object as defined by the interceptor's specification. The method defined on an interceptor class must have one of the following signatures: void method invocation context, object method invocation context throws exception. Note: predestroy interceptor method must not throw application exceptions, but it may be declared to throw checked exceptions, including java.lang.exception if the same interceptor method interposes on business or timeout method in addition to lifecycle events. If a predestroy interceptor method returns a value, it is ignored by the container. The method defined on a non-interceptor class must have the following signature: void method open bracket close bracket. The method on which predestroy is applied may be public, protected, package private, or private. The method must not be static. The method may be final. If the method throws an unchecked exception, it is ignored except in the case of EJBs, where the EJB can handle exceptions. Void destroy, invoked by containing bean factory on destruction of a bean. And we are considering lifecycle callbacks. To interact with containers management of bean lifecycle, you can implement Spring initializing bean and disposable bean interfaces. The container calls after property set for former and destroy for the latter to let the bean performs certain actions upon initialization and destruction of beans. If you, the JSR 250 at post construct and pre-destroy annotations are generally considered best practice for receiving lifecycle callbacks in modern Spring application. Using these annotations means that your beans are not coupled with Spring specific interfaces. You do not if you do not want to use JSR 250 annotation but still want to remove coupling, consider init method and destroy method, bean definition metadata. Internally, Spring Framework uses bean post processor implementations to process any callback interfaces that can find and call the appropriate method. If you need custom features or other lifecycle behavior Spring does not by default offer, you can implement bean post processor by yourself. In addition to initialization and destruction callbacks, Spring Manage object may also implement the lifecycle interface so that those objects can participate in startup and shutdown process as driven by container's own lifecycle. Initialization callbacks. The org.springframework.beans.bean factory.initializing bean interface lets a bean perform initialization work after the container has set all necessary properties on the bean. The initializing bean interface is specified a single method, void after properties throws exception. We recommend that you do not use initializing bean. We recommend that you do not use initializing bean interface because it unnecessarily couples the code to Spring. Alternatively, we suggest using the at post construct annotation or specifying POJO initialization method. In this case, XML based configuration metadata, you can use init method attribute to specify the name of the method that has a void no argument signature. With Java configuration, you can use init method attribute of @beans. Destruction callbacks. Implementing the org.springframework.beans.factory.disposable bean interface lets a bean get callback when a container that contains it is destroyed. The disposable bean interface specifies a single method, void destroy throws exception. We recommend that you do not use the disposable bean callback interface because it unnecessarily couples the code to Spring. Alternatively, we suggest using the at pre-destroy annotation or specifying generic method that's supported by bean definitions. With XML configuration metadata, you can use destroy method attribute on the bean. With Java configuration, you can use destroy method attribute @bean. Default initialization and destroy methods. When you write initialization and destroy methods callbacks that do not use the Spring specific initializing beans or disposable bean callback interfaces, you typically write methods with names such as init method, initialize method, dispose method, and so on. Ideally, the names of such lifecycle callbacks method are standardized across a project so that all developers use the same method names and ensure consistency. You can configure the Spring container to look for names named initialization and destroy callback method names for every bean. This means that you, as an application developer, can write your application classes and use an initialization callback called init method without having to configure an init method equal init attribute with each bean definition. The Spring IOC container calls that method when the bean is created. This feature also enforces a consistent naming convention for initialization and destroy callbacks. combining lifecycle mechanisms, as of Spring 2.5, you have three options for controlling bean lifecycle behavior: the initializing bean and disposable bean callback interfaces, custom init and destroy method, the post construct the at post construct and at pre-destroy annotations. You can combine these mechanisms to control given bean. If multiple lifecycle mechanisms are configured for a bean, and each mechanism is configured with a different method name, and each configured method is run in the order listed after. However, if the same method name is configured, for example, init method for an initialization method, for more than one of these lifecycle mechanisms, that method is run once. Multiple lifecycle mechanisms configured for the same bean with different initialization method are called as follows. First, the methods annotated with at post construct. Step 2, then after properties set method is defined by initializing bean callback interface. Step 3, the custom configured init method. Destroy methods are called in the same order. Step 1, method annotated with pre-destroy at pre-destroy. Step 2, destroy method as defined by the disposable bean callback interface. Step 3, a custom configured destroy method. And with the startup and shutdown callbacks, the lifecycle interface define essential methods for any object that has its own lifecycle requirements. As such, starting, stopping some background processes. There are in the interface. There are methods: void start method, void stop method, and boolean is running method. Here you can see construct is connected to setter method. Setter method is connected to bean name aware dot set bean name method. Bean class loader aware dot it is connected to bean class loader aware dot set bean class loader method. It is connected to bean factory aware dot set bean factory method. It is connected to this is connected to post bean bean post processor dot post process before initialization method. This is connected to at post construct. At post construct is connected to initializing bean dot after properties set method, and this is connected to init method. Init method is connected to bean post processor dot post process after initialization method, and it is connected to bean is performing task. Bean ready to use is passed from bean post processor dot post process initialization method to post process after initialization method to bean is performing task. Bean is performing task is connected to at pre-destroy. IOC container about to remove bean is passed from bean is performing task to at pre-destroy. At pre-destroy is connected to disposable bean dot destroy method. Disposable bean dot destroy method is connected to destroy method. Destroy is connected method is connected to finalize method. Here following image shows how the singleton scope works. Only one shared instance of a singleton bean is managed, and all requests for beans with IDs or ID or IDs that match that bean definition result that one specific bean instance being returned by the Spring container. To put in another way, when you define the bean definition and its scope as a singleton, the Spring IOC container creates exactly one instance of the object defined by that bean definition. The single instance is stored in a cache of such singleton beans, and all subsequent requests and references for that named bean return the cached object. Following image shows how the singleton scope works. Spring's concept of singleton bean differs from the singleton pattern as defined in the Gang of Four GOF patterns book. The GOF singleton hardcodes the scope of an object such that one and only one instance of a particular class is created per class loader. The scope of Spring singleton is best described as per container and per bean. This means that if you define one bean for a particular class in a single Spring container, the Spring container creates one and only one instance of the class defined by that bean definition. The singleton scope is the default scope in Spring. Here you can see account DAO. Only one instance is ever created, and this same shared instance is injected into collaborating objects. And this bean is connected to these beans. The following diagram illustrates the Spring prototype scope. The non-singleton prototype scope of bean deployment result in the creation of a new bean instance every time a request of that specific bean is made. That is, the bean is injected into another bean, or your request it through a get bean method call on the container. As a rule, you should use the prototype scope for all stateful beans and singleton scope for stateless beans. Following diagram illustrates the Spring prototype scope. The data access object DAO is not typically configured as a prototype because the typical DAO does not hold any conversational state. It was easier for us to reuse the core of the singleton diagram. In contrast with other scopes, Spring does not manage the complete lifecycle of a prototype bean. The container instantiate, configures, and otherwise resembles a prototype object and hands it to the client. With no further record of that prototype instance. Thus, although initialization lifecycle callback methods are called on all objects regardless of scope, in the case of prototype, configured destruction lifecycle callbacks are not called. The client code must clean up prototype scope, clean up the prototype scope object and release expensive resource that the prototype beans hold. To get the Spring container to release resources held by prototype scope beans, try using custom bean post processor, which hold a reference to beans that need to be cleaned up. In some respects, Spring container's role in regard to prototype scope bean is replaced for Java new operator. All lifecycle management past that point must be handled by the client. Here brand new bean instance is created each and every time the prototype is referenced by collaborating beans. Here bean 1 is connected to this bean, and bean 2 is connected to this bean, and bean 3 is connected to this bean of prototype. As an example, we can consider this Maven segment. Artifact ID spring beans. Spring Beans provides the configuration framework and basic functionality to instantiate, configure, and assemble Java objects. As an example 2, we can consider package org.springframework.beans. This package contains interfaces and classes for manipulating Java beans. As an example 3, we are considering instantiation with the constructor in bean overview. With XML based configuration metadata, you can specify your bean class as follows. When you create a bean by the constructor approach, all normal classes are usable by and compatible with string. That is, the class being developed does not need to implement any specific interfaces or to be coded with specific fashion. Simply specifying the bean class should suffice. However, depending on what type of IOC you use for that specific bean, you may need the default empty constructor. In Spring IOC container can manage virtually any class you want it to manage. It is not limited to managing true Java beans. Most Spring users prefer actual Java beans by only a default no argument constructor and appropriate setters and getters modeled after properties in the container. You can also have more exotic non-bean style classes in your container. If, for example, you need to use a legacy connection pool that absolutely does not adhere to the Java bean specification, Spring can manage it as well. With XML configuration metadata, you can specify your bean class as follows here. As an example, we are considering dependency injection in dependencies. The following examples uses XML based configuration metadata for setter based DI. A small part of Spring XML configuration file specifies the some bean definitions as follows. The following example shows the corresponding example bean. And also we can focus on dependency resolution process. The container performs bean dependency resolution as follows. The application context is created and initialized with configuration metadata that describe all beans. Configuration metadata can be specified by XML, Java code or annotation. For each bean, its dependencies are expressed in the next point, each bean dependencies are expressed in the form of properties, construct arguments, or arguments to the static factory method. If you use that instead of a normal constructor, these dependencies are provided to the bean when bean is actually created. The next next point is each property or constructor argument is an actual definition of the value is set or reference to another bean in the container. Each property or constructor argument that is a value is converted from a specific converted from its specified format to actual type of the property or constructor constructor types. Property or constructor argument. By default, Spring can convert a value supplied in a string format to all built-in types such as int, long, string, bean, and so forth. Spring container validates the configuration of each bean as the container is created. However, the bean properties themselves are not set until the bean is actually created. Beans that are singleton scoped and said to be pre-instantiated, the default are created when the container is created. Scopes are defined in bean scopes. Otherwise, the bean is created only when it is requested. Creation of a bean potentially causes a graph of beans to be created as beans dependencies and its dependencies and so on are created and assigned. Note that the resolution mismatches among those dependencies may show up late, that is, on first creation of affected bean. Setter injection using the nested ref element. Setter injection using neater ref attributes. In this example, setters are declared to match against the property specified in the XML file. Following example uses constructor-based dependency injection. This example shows corresponding example bean class. The constructor arguments Construct arguments specified in the bean definition are used as argument to the construct of example bean. Construction injection using nested ref element. Construct injection using the neater ref attribute. Now consider a variant of this example where instead of using a constructor, Spring is told to call a static factory method to return an instance of the object. The following example shows corresponding example bean class. The arguments to static factory method are supplied by constructor args elements exactly as the same the same as if the constructor had actually been used. The type of the class being returned by the factory method does not have to be the same type of the class that contains the static factory method, although it in this example it is. An instance non-static factory method can be used essentially identical fashion aside from the use of the factory bean attribute instead of a factory bean attribute instead of the class attribute. So we do not discuss those details here. A private constructor. A static factory method, the argument to this method can be considered the dependencies of the bean that is returned regardless of how those arguments are actually used. Some other operations. Following example uses the p namespace for more succinct XML configuration. As an example 7, we are considering singleton scope in bean scopes. To define a bean as a singleton XML, a singleton in XML, you can define a bean as shown in the following example. Following is equivalent, though redundant. Singleton scope is the default. The following example defines a bean as a prototype XML. Now we are considering using a custom scope. You can also do scope registration declaratively by using custom scope configurer class, as following example shows. The class custom scope configurer, simple bean factory post processor implementation that registers the custom scopes with the containing configurable bean factory. This is in the package org.springframework.beans.factory.config. After you write and test one or more custom scope implementations, you need to make the Spring container aware of your new scopes. The following method is the central to register a new scope with the Spring container. Void register scope, string scope name, scope. This method is declared on the configurable bean factory interface, which is available through bean factory property on most of the concrete application context implementation that ship with the string. The first argument to the register scope method is the unique name associated with the scope. Examples of such names in Spring contain itself are singleton and prototype. Such argument to second argument to register scope method is an actual instance of the custom scope implementation that you wish to register and use. Suppose you write to a custom scope implementation and then register it as shown here. Here this uses simple thread scope, which is included with Spring but not registered by default. The instruction would be same for your own custom scope implementations. You can then create bean definitions that adhere to the scoping rules of your custom scope, like here. With the custom scope implementation, you are not limited to programmatic registration of the scope. You can also do scope registration declaratively by using custom scope configurer class, as the following example shows. when you place AOP colon scope proxy within a bean, declaration for factory bean implementation, that is factory bean itself, that is not that is scoped, not the same object returned from get object. We are considering initialization callback in lifecycle callbacks in customizing nature of the bean. Consider the following example. In case of XML based configuration metadata, you can use init method here. Init method attribute to specify the name of the method that has a void no argument signature. This example yeah. Do some initialization work here. Here with initialization callback, we are considering basically after property set method in org.spring framework.beans.factory.initialization bean, but here we are providing this example as an alternative approach. As an example 11, we are considering bean definition inheritance. Following example shows how to do so. A bean definition can contain a lot of configuration information, including constructor, arguments, property values, contain specific information such as initialization method, a static factory method name, so on. Child bean definition inherits configuration data from parent definition. Child definitions can override some values or add others as needed. Using parent and child bean definitions can save a lot of typing. Effectively, this is a form of templating. If you work with an application context interface programmatically, child bean definitions are represented by child bean definition class. Most users do not work with them on this level. Instead, they configure bean definitions declaratively in a class such as class path XML application context. When you use XML based configuration metadata, you can indicate a child bean definition by using parent attribute, specifying parent bean as a value of this attribute. The following example shows how to do so. Here note the parent attribute. Child bean definitions uses child bean definition uses bean class from the parent definition. If none is specified but can override it. In latter case, the child bean class must be compatible with the parent. That is, it must accept parent's property values. Child bean definition inherit scope. Construct argument values, property values, and method overrides from parents with option to add new values. Any scope initialization methods, destroy method or static method settings that you specify override the corresponding parent settings. The remaining settings are always taken from the child definition, depends on auto-wired mode, dependency check, singleton, and lazy init. In this example, this is explicitly marks the parent bean definition as abstract by using abstract attribute. If the parent definition does not specify a class, explicitly marking the parent bean definition as abstract is required. Application context instantiates all singletons by default. Therefore, it is important, at least for a singleton beans, that if you have a parent bean definition which you intend to use only as a template, and this definition specify a class, you must make sure to set the abstract attribute to true. Otherwise, the application context will actually attempt to pre-instantiate the abstract bean. The age property of value 1 will be inherited from the parent. As an example 12, we are considering customizing beans by using a bean post processor in contain extension point. Following listing shows the custom bean post processor implementation class definition. Interface bean post processor factory hook that allows for custom modification of new bean instances, for example checking for marker interfaces or wrapper beans with proxies. This is in the package org.springframework.beans.factory.config. This example illustrates the basic usage. The example shows custom bean post processor implementation that invokes toString method of each bean. As it is created by container and prints the resulting string to the system console. The following listing shows the custom bean processor implementation class definition. The following bean element uses the following bean element uses instantiation tracing bean post processor. Notice how the instantiation tracing bean post processor is merely defined. It does not even have a name, and because it's a bean, it can be dependency injected as you would any other bean. This example also this configuration also defines a bean that is backed by a groovy script. Simply return instantiated bean as is. We could potentially return any object reference here. When the above bean messenger is instantiated, the custom bean post processor implementation will output the fact to the system console. The following application runs the previous code and configuration. The output of the application resembles as following. As an example 13, we are considering annotation based container configuration. Are annotations better than XML for configuring Spring? The introduction of annotation based configuration raised a question of whether the approach is better than XML. The short answer is it depends. The long answer is that each approach has its pros and cons, and usually it is up to the developer to decide which strategy suits them better. Due to the way they define, annotations provide a lot of context in their declaration, leading to shorter and more concise configuration. However, XML excels at wiring up components without touching their source code or recompiling them. Some developers prefer having wiring code to the source, while others argue that annotated classes are no longer POJOs, and furthermore that configuration becomes decentralized and harder to control. No matter of choice, Spring can accommodate both styles and even mix them together. It is worth pointing out that through its Java config option, Spring lets annotations be used in a non-invasive way without touching the target component source code, and that in terms of tooling, all configuration styles are supported by Spring tools for Eclipse. An alternative XML setup is provided by annotation-based configuration, which relies on the bytecode metadata for wiring up component instead of angle bracket declarations. Instead of using XML to describe bean describe a bean wiring, the developer moves the configuration into component class itself by using annotations on the relevant class, method, or field declaration. For example, Spring 2.5 introduced an annotation-based approach to drive Spring dependency injection. Essentially, the AutoWide annotation provide the same capabilities as described in auto-wiring collaborations, but with more fine-grained control and wider applicability. Spring 2.5 also added support for JSR 250 annotations such as at post construct and at pre-destroy. Spring 3.0 added support for JSR 330 dependency injection for Java annotations contained the Jakarta.inject package such as at inject and at named. Annotation injection is performed before XML injection. Thus, XML configuration overrides the annotation for properties wired through both approaches. As always, you can register the post processors as individual bean definition, but they can be implicitly registered by including following XML tag in XML based configuration. Notice the inclusion of context namespace. The context colon annotation config element implicitly registers the following post processors: configuration class post processor, auto-wired annotation bean post processor, common annotation bean post processor, persistent annotation bean post processor, event listener method processor. Context colon annotation config only looks for annotations on beans in the same application context in which it is defined. This means that if you put context annotation config in a web application context for a dispatcher servlet, it only checks the auto-wired beans for your controllers and not your services. The at required annotation applies to a bean property setter methods as in the following example. The annotation type required marks a method, typically a Java bean setter method, as being required. That is, the setter method must be configured to be dependency injected with the value. This is in the package org.springframework.beans.factory annotation. As an example 15, we are considering dependency injection with at inject and at named. Here we are considering at inject using JSR 313 standard annotation. Instead of auto-wired, you can use at Jakarta you can use at Jakarta inject as follows. Annotation type inject. Identify the injectable constructors, methods and fields that may apply to static as well as instance members. An injectable member may have any access modifier: private, package, private, protected, public. Constructors are injected first by fields and then methods. The fields and methods are in superclasses are injected before those in subclasses. Ordering of injection among fields and among methods in the same class is not specified. This is in the package Jakarta.inject. As with auto-wired, at auto-wired you can use at inject in the field level, method level, and constructor argument level. Furthermore, you may declare injection point as a provider, allowing on-demand access to beans of short scopes or lazy access to other beans through a provider.get call. As an example 16, we are considering Bean Factory or application context in Bean Factory API with related to Bean Factory API. Here we explain the difference between the Bean Factory and to explicitly register a bean post processor with the default listable bean factory. You need to programmatically call add bean post processor as following example shows here. Class default listable bean factory springs default implementation of the configurable listable bean factory and bean definition registry interfaces. The full fledged bean factory based on bean definition metadata extensible through post processors. This is in the package org.springframework.beans.factory.support. So here we are explaining the difference between bean factory and application context container levels and implications on bootstrapping. You should use application context unless you have a good reason for not doing so. With generic application context and its subclass annotation config application context as common implementation for custom bootstrapping. There are these are the primary entry points for Spring's core container for all common purposes. Loading of configuration files triggering a class path scan, programmatically registering bean definitions and annotated classes, and as of 5.0 registering functional bean definitions. Because application context includes all the functionality of a factory bean, it is generally recommended over a plain bean factory, except for scenarios where full control over bean processing is needed. With an application context such as generic application context implementation, several kinds of beans are detected by convention, that is by bean name and by bean type, in particular post processors, while a plain default list bean factory is agnostic about any special beans. For many extended container features such as annotated processing and AOP proxy, the bean post processor extension point is essential. If you only use a plain default listable bean factory, such as post processors do not get detected and activated by default, the situation could be confusing because nothing is actually wrong with your bean configuration. Rather, in such scenario, the container needs to be fully bootstrapped through additional setup. Explicitly register a bean post processor with default listable bean factory, you need to programmatically call add bean post processor as following example shows here. Populate factory with bean definitions. Now register any needed bean post processor instances. Now start using the factory. As an exception example, we can consider beans exception. Class beans exception. Abstract superclass for all exceptions thrown in the beans package and subpackages. Org Spring Framework beans package contains this class. As an error example, we can consider this error message. This is occurred, for example, bean A is trying to inject bean B here, and copy if bean B isn't found in the context, then the following exception will be thrown: error creating bean. So the error creating bean with the name bean A, injection of auto-wide dependencies failed. Nested exception of is org.spring framework.beans.factory. Bean creation exception could not auto-wire field private and etc. Now we are focusing on core. The Spring Core and Spring Beans modules provide the fundamental parts of the framework, including the IOC and dependency injection features. As an example, we can consider this Maven segment. Here you can see artifact ID Spring-Core. Spring Core, basic building block for Spring that in conjunction with Spring Beans provides dependency injection and IOC features. This is in the group ID org.spring framework. As an example too, we can consider package org.springframework.core provides basic classes for exception handling and version detection, and other core helpers that are not specific to any part of the framework. As an example 3, we can consider following packages: org.springframework.asm, Spring's repackaging of ASM 9.x with the Spring specific patches for internal use only. Package org.springframework.cglib, Spring's repacking of cglib 3.3 with Spring specific patches for internal use only. Package org.springframework.lang, common annotations with language level semantics, nullability as well as JDK API indications. These annotations sit at the lowest level of Spring package dependency arrangement, even lower than org.springframework.util with no Spring specific concepts implied. Package org.springframework.obgenesis, Spring's repackaging of obgenesis 3.2 with Spring obgenesis entry point for internal use only. Package org.springframework.util, miscellaneous utility classes such as utilities for working with strings, classes, collections, reflection, etc. As an example 4, we are considering convert SPI in Spring type conversion. The following listing shows string to integer class, which is a typical converter implementation. Interface converter ST. This is a functional interface and there can therefore be used as a assignment target for lambda expression for or method reference. This is in the package org.springframework.core.convert.converter. The SPI to implement type conversion logic is simple and strongly type. To create your own converter, implement converter interface and parameterize S as the type you are converting from, and T as the type you are converting to. You can also transparently apply such a converter if the collection or array of S need to be converted to an array or collection of T, provided that the delegating array or collection converter has been registered as well, which default conversion service does by default. For each call to convert S, the source argument is guaranteed to not to be null, and your converter may throw an unchecked exception if the conversion fails. Specifically, it should not throw an illegal argument exception to report an invalid source value. Take care to ensure that your converter implementation is thread safe. Several convert implementations are provided in the core.convert.support package as a convenience. These include converters from single strings to numbers and other common types. The following listing shows a string to integer class, which is a typical converter implementation. As an example 5, we are considering ordered, and we are focusing on using @AutoWired in container annotation-based container configuration. Your target beans can implement org.springframework.core.ordered interface or use @order or standard @priority annotation if you want items to the array or list to be sorted in a specific order. The interface ordered is an interface that can be implemented by objects that should be orderable, for example, in a collection. This is in the package org.springframework.core. Your target beans can implement the org.springframework.core.ordered interface or use @order or standard @priority annotation if you want items in the array or list to be sorted in a specific order. Otherwise, their order follows the registration order of the corresponding target bean definitions in the container. You can declare @order annotation at the target class level and on bean methods, potentially for individual bean definitions. In case of multiple definitions that use the same bean class, @order values may influence priorities at injection points, but be aware that they do not influence singleton startup order, which is an orthogonal concern determined by dependency relationships and depends on declarations. Note that the standard Jakarta.annotation.priority annotation is not available at bean level since it cannot be declared on methods. Its semantics can be modeled through @order values in combination with at primary on a single bean for each type. In an example 6, we are considering using filters to customize scanning in class path scanning and manage components. We are considering here interface type filter. This is a functional interface and can therefore be used as a assignment target for lambda expression or method reference. This is in the package org.springframework.core.type.filter. As an example 7, we are considering the resource loader interface as a topic. Here, for example, assume the following snippet of code and was run against a class path XML application context instance. Here you can see the interface is resource. Interface for a resource descriptor that abstract from the actual type of underlying resource, such as a file or a class path resource. This is in the package org.springframework.core.io. The resource loader interface is meant to be implemented by objects that can return, that is, load resource instances. The following list resources. All application context implement the resource loader interface Therefore, all application contexts may be used to obtain resource instances. When you call get resource on a specific application context and the location path specified does not have a specific prefix, you get back a resource type that is appropriate to that particular application context. For example, assume the following snippet of code was run against the class path XML application context instance. Against the class path XML application context, that code returns class path reference, class path resource, if the same method were run against the file system XML application context instance, it would return a file system resource. For a web application context, it would return a servlet context resource. It would similarly return appropriate object for each context. As a result, you can load resources in a fashion appropriate to a particular application context. As an example 8, we are considering here type conversion in understanding evaluation context in evaluation in Spring Expression Language, SpEL. SpEL recognizes that the element of the list need to be converted to Boolean before being placed it in. The following example shows how to do so. Interface conversion service service interface for type conversion. This is the entry point into the conversion system. Call convert object class to perform thread safe type conversion using this system. This is in the package org.springframework.core.convert. By default, SpEL uses the conversion service available in Spring Core, org.springframework.core.convert.conversion service. This conversion service comes with many built-in converters for common conversions, but is also fully extensible so that you can add custom conversions between types. Additionally, it is generics aware. This means that when you work with generic types in expressions, SpEL attempts conversions to maintain type correctness for any objects it encounters. What does this mean in practice? Suppose assignment using setValue is being used to set the list property. The type of the property is actually list Boolean. SpEL recognizes that element of the list needs to be converted to Boolean before being placed it in. The following example shows how to do so. False is passed here as a string. SpEL and conversion service will recognize that it need to be a Boolean and convert it accordingly. B is false. Um, the org.spring framework codec package provides the following strategic interfaces: encoder to encode publisher T into a stream of data buffers, encoder to encode publisher data buffer into a stream of higher level objects, package org.spring-framework.codec encoder and decoder abstractions to convert between reactive stream of bytes and Java objects. The Spring Core module provides byte array, byte buffer, data buffer, resource, and string encoder decoder implementations. Spring Web module adds JSON, Jackson Smile, JAX B2, protocol buffers, and other encoders and decoders. As an example 10, we are considering using a task executor. Using a task executor in task execution, and scheduling. In the following example, we define a bean that uses the thread pool task executor to asynchronously print out a set of messages. The interface task executor, simple task executor interface that abstracts the execution of a runnable. This in the package org.springframework.core.task. Spring's task executor implementations are used as simple Java beans. In the following example, we define a bean that uses thread pool task executor to asynchronously print out a set of messages. As you can see, rather retrieving thread from the pool and executing it yourself, you can add your runnable to the queue. Then the task executor uses its internal rules to decide when to task get run. To configure rules for the task executor users, we expose simple bean properties. As an example 11, we are moving into transaction management. The following code shows a simple profiling aspects. Here you can see class stopwatch, simple stopwatch allowing for timing of a number of tasks, exposing total running time and running time for each named task. Allow us to control the ordering of the advice here. This method is the around advice. As an exception example, we can consider this. By default, those are set to 256 KB. If that's not enough, you will get the following error here. The class buffer limit exception that indicates the cumulative number of bytes consumed from a stream of data buffers exceeded some pre-configured limit. This can be raised when data buffers are cached and aggregated. For example, data buffer units.join org.reactivestreams.publisher question extend org.springframework.core.io.buffer.data buffer, or it could be also be raised when data buffers have been released but a past representation is being aggregated. For example, async parsing with Jackson, SSC parsing and aggregating lines per event. This in the package springframework.core.io.buffer, and here you can see exceeded limit on max byte to buffer. As an error example, we can consider this error occurred in an environment with Spring, JPA, MySQL, and Tomcat. Here you can see exception encountered during context initialization, cancelling, refresh attempts, etc. And here you can see nested exception is java.lang.no such method error in org.springframework core.log delegate factory.get hidden log l java lang string l org apache commons logging log etc. Now we are focusing on context. The context Spring context module builds on the solid base provided by the core and beans modules. It is a means to access objects in a framework style manner that is similar to a JNDI registry. The context module inherits its features from the beans module and adds support for internationalization using, for example, resource bundles, event propagation, resource loading, and transparent creation of context by, for example, a servlet container. The context module also supports Java EE features such as EJB, JMX, and basic remoting. The application context interface is the focal point of the context module. Spring Context Support provides support for integrating common third-party libraries into a Spring application context, in particular for a caching, EHCache, JCache, and scheduling common J quartz. Here you can see the Spring IOC container. The container overview, the org.springframework.context.application context interface represents the the Spring IOC container, and is responsible for instantiation, configuring and assembling the beans. Container gets its instruction on what objects to instantiate, configure and assemble by reading configuration metadata. The configuration metadata is represented in XML, Java annotations or Java code. It lets you to express the objects that compose your application and rich dependencies between those objects. Several implementations of the application context interface are supplied with Spring. In standalone application, it is common to create an instance of class path XML application context or file system XML application context. While XML has been the traditional format for defining configuration metadata, you can instruct the container to use the Java annotations or code as the metadata format by providing a small amount of XML configuration to declaratively enable support for those additional metadata formats. In most application scenarios, explicit user code is not required to instantiate one or more instances of Spring IOC container. For example, in a web application scenario, a simple 8 or so lines of boilerplate web descriptor XML in the XML web.xml file of the application typically suffices. If you use the Spring tools for Eclipse, an Eclipse powered development environment, you can easily create this boilerplate configuration with a few mouse clicks or keystrokes. This diagram shows a high-level view of how Spring works. Your application classes are combined with configuration metadata, so that after the application context is created and initialized, you have fully configured and executable system or application. Here you can see your business objects, POJOs are connected to are passed to Spring container. Configuration metadata is passed to the Spring container. The Spring container is connected to fully configured system ready for use. Producers is passed from Spring container produces a fully configured system ready to use. Here you can see the servlet specific child web application context, which typically contains beans local to the given servlets. The following image shows this relationship. In context hierarchy, the dispatch servlet expects a web application context, an extension to the plain application context for its own configuration. Web application context has a link to servlet context, and the servlet with which it is associated. It is also bound to servlet context, such as applications can use statics method on result context utils to look up the web application context if they need access to it. For many applications, having a single web application context is simple and suffices. It's also possible to have a context hierarchy where one root web application context is shared across multiple dispatch servlets or other servlet instances, each with its own child web application context configuration. The root web application context typically contains infrastructure beans such as data repositories, and business services that need to be shared across multiple servlet instances. Those beans are effectively inherited and can be overridden, that is redeclared in the servlet specific child web application context, which typically contains beans local to the given servlets. The following image shows this relationship. Here you can see the dispatcher servlet, and inside it you can see a servlet web application context containing controllers, view resolvers, and other web-related beans. You can see controllers, web resolver, and handler mappings are inside the servlet web application context. Servlet web application context is connected to root web application context. A delegate, if no bean found, is passed from servlet web application context to root web application context. Root web application context containing middle tier services, data sources, etc. Services and repositories are inside the web root application context. Here you can see a parent and child context. We have seen two major types of context: the root web application context and dispatcher servlets context. Then we might have a question: are those contexts related? It turns out that yes, they are. In fact, the root context is the parent of every dispatcher servlet context. Thus, beans defined in the root web application context are visible in each dispatcher servlet context, but not vice versa. So typically the root context is used to define service beans, while the dispatcher context contains those beans that are specifically related to MVC. Note that we have seen ways to create the dispatcher servlets context programmatically. If we manually set this its parent, then Spring does not override our decision, and this section no longer applies. In simpler MVC applications, it is sufficient to have single context associate only with one dispatcher servlet. There is no need for overlay complex solutions. Still, parent-child relationship becomes useful when we have multiple dispatcher servlets configured. But when should we bother to have more than one? In general, we declare multiple dispatcher servlets when we need multiple sets of MVC configurations. For example, we may have REST API alongside the traditional MVC application, an unsecured and a secure section of a website. And not when we extend abstract dispatcher servlet initializer, we register both a root web application context and a single dispatcher servlet. So if we want more than one servlets, we need multiple abstract dispatcher servlet initialize implementations. However, we can only define one root context or the application won't start. Fortunately, a create root application context method can return null. Thus, we can have one abstract context loader initializer and many abstract dispatcher servlet initializer implementation that don't create the root context. In such scenario, it is advisable to order the initializers at order explicitly. Not Also note that abstract dispatcher servlet initializer registers the servlet under a given name, dispatcher, and of course we cannot have multiple servlets with the same name, so we need to overwrite get servlet name. Here you can see dispatcher servlet A and control is inside it, and here you can see dispatcher servlet B, controller is inside it, and those are connected to a root web application context. You can see the service is inside the root web application context. As an example, we can consider this Maven segment. Here you can see artifact ID, Spring context. Spring context provides access to a configured object like a registry, a context. It inherits its features from Spring Beans and adds support for internationalization, event propagation, resource loading, and transparent creation of context. This is in the group ID org.spring framework. As an example too, we can consider package org.springframework.context. This package builds on the Beans package to add support for message sources and for the observer design pattern, and the ability for application objects to obtain resources using a consistent API. As an example 3, we can consider interface application context, and we are here considering introduction to IOC container and Beans and container overview here as a topic. And application context is a sub interface of Bean Factory. Interface application context, central interface to provide configuration for an application. This is read only while the application is running, but may be reloaded if the implementation supports this. This in the package org.springframework.context. IOC is also known as dependency injection, DI. It is a process whereby objects define their dependencies, that is other objects they work with, only through construct arguments to a factory method, or properties that are set on the object instance after it is constructed or returned from a factory method. The container then injects those dependencies when it creates the bean. This process is fundamentally the inverse, hence the name inversion of control of the bean itself, controlling the initial instantiation or location of its dependencies by using direct construction of classes or a mechanism such as the service locator pattern. The org.springframework.beans and org.springframework.context packages are basis for Spring Framework's IOC container. The Bean Factory interface provides an advanced configuration mechanisms capable of managing any type of object. Application context is a sub-interface of Bean Factory. It adds easier integration with Spring's AOP features, message resource handling for using internationalization, event publication, application layer specific context such as web application context for use in web applications. In short, the Bean Factory provides the configuration framework and basic functionality, and the application context at the more enterprise specific functionality. The application context is more complete superset of the Bean Factory and is used exclusively in Spring's IOC container. In Spring, the objects that form the backbone of your application and that are managed by the Spring's IOC container are called beans. A bean is an object that is instantiated, assembled, and managed by IOC container. Otherwise, a bean is simply one of many objects in your application. Beans and the dependencies among them are reflected in the configuration metadata by a container. As an example, we are considering method injection in dependencies. A solution to forego some inversion of control, you can make a bean aware of container by implementing application context aware interface, and by making get bean b to call to the container, asks for a typically new bean instance every time bean a needs it. The following example shows this approach. The interface application context aware interface to be implemented by any object that wishes to be notified of the application context that's run in it. This is in the package org.spring framework.context. In most scenarios, the most beans in the container are singletons. When a singleton bean needs to collaborate another singleton bean, or non-singleton bean needs to collaborate with another non-singleton bean, you typically handle a dependency by defining one bean as a property of the other. A problem arises when bean life cycles are different. Suppose singleton bean A needs to use non-singleton bean prototype bean B. Perhaps each method invocation on A, the container creates a singleton bean A only once, thus only get one opportunity to get set properties. The container cannot provide bean A with a new instance of the bean B every time once it is needed. The solution is to forego some inversion of control. You can make bean A aware of the container by implementing application context aware interface, and then by making get bean B call to the container, ask for a typically new bean instance every time bean A needs it. The following example shows this approach. This example is not desirable because the business code is aware of and coupled with Spring framework. Method injection is somewhat advanced feature of the IOC container. Let's see how to handle this use case cleanly. So we are here focusing on application context aware. So you can check method injection separately. Grab a new instance of the appropriate command. Notice the Spring API dependency. Set the state on the hopefully brand new command instance. Here you can see using custom scope in bean scopes. You can also scope registration declaratively by using custom scope configure class, as the following example shows. Here we are focusing on class simple thread scope, a simple thread backed scope implementation. This is in the class, this is in the package Spring framework.context.support. As an example 6, we are considering class name substitution, property sources placeholder configurer in container extension points. Consider the following XML based configuration metadata fragment where data source with placeholder values defined. The class property sources placeholder configurer specialization of placeholder configurer support that resolves $ open curly brace and then close curly brace placeholders within bean definition property values and at value annotations against the current Spring environment and its set of property sources. This is in the package Spring framework.context.support. You can use property source placeholder configurer to externalize property values from the bean definition in a separate file by using standard Java properties format. Doing so enables the person deploying the application to customize environment specific properties such as database URLs and passwords without complexity or risk of modifying the main XML definition file or files for the container. Consider the following XML based configuration metadata fragment where the data source with placeholder values defined. Example the example shows properties configured from external properties file. At runtime, the property sources placeholder configurer is applied to the metadata and replaces some properties of the database. Properties of the data source. The values to replace are specified as placeholder is of the form $ open curly brace property name and close curly brace, which follows the ANT and log4j and JSP-EL style. The actual values come from another file in the standard Java properties format. Therefore, the $ open curly brace jdbc.username close curly brace string is replaced at runtime with the value SA, and the same applied for other placeholder values that match keys of the properties file. The property source sources placeholder configurer checks for placeholders in most properties and attributes for bean definition. Furthermore, you can customize the placeholders prefix and suffix. With the context namespace introduced in Spring 2.5, you can configure the property placeholders with the dedicated configuration element. You can provide one or more locations as a comma separated list in the location attributes, as the following example shows here. The property sources placeholder configurer not only looks for properties in the properties file you specify. By default, it can find a property in the specified properties file. It checks against Spring environment properties and regular Java system properties. You can use the property sources placeholder configurer to substitute class names, which is sometimes useful when you have to pick a particular implementation class at runtime. If the class cannot be resolved at runtime to a valid class, resolution of the bean fails when it is about to create. about to be created, which is during pre-instantiate singleton space of the application context for non-lazy init bean. Now we are focusing on here class path scanning and manage component. Here provide the fully qualified class name when configuring the scanner, as the following example annotations and bean definition shows. The annotation type component scan configures the annotation type component scan configured the component scanning directives for use with at configuration classes, provide support for parallel with Spring XML's context component scan element. This is in the package auxiliary spring framework.context.annotation. Here you can see fully qualified class name. As an example 8, we can consider Java-based container configuration. Here we are focusing on at configuration. The simplest possible at configuration class reads as follows. The annotation type configuration indicates that a class declares one or more @bean methods and may process by the Spring container to generate bean definitions and service requests for those beans at runtime. For example, this is in the package org.springframework.context.annotation. The central artifacts in Spring's new Java configuration supports are at configuration annotated classes and at bean annotated methods. At bean annotation is used to indicate that the method instantiate configures and initializes a new object to be managed by the Spring IOC container. For those familiar with Spring's beans XML configuration, the at bean annotation plays the same role as the bean element. You can use the at bean annotation methods with any Spring at component. However, are most used by the at configuration beans. Annotating class with at configuration indicates that its primary purpose is as source bean definitions. Furthermore, at configuration class let inner bean dependencies be defined by calling other at bean methods in the same class. The simplest possible at configuration class read as follows. The preceding app config class is equivalent to the following Spring Bean XML. Full at configuration versus light at bean mode. When at bean methods are declared within the classes that are not annotated with that configuration, they are referred to as bean process as light mode. Bean methods declared in at components or even on a plain old classes are considered to be light, with different primary purpose of containing class and at bean method being short of bonus here. For example, service component may expose management views to the container through the additional at bean method and on each applicable component class. In such scenarios, at bean methods are general purpose factory method mechanism. Unlike full at configuration, light at bean methods cannot declare inner bean dependencies. Instead, they operate on their containing components internal state and optionally on arguments that they may declare. Such at bean method should therefore not invoke other at bean methods. Each such method is literally only a factory method for particular bean reference without any special runtime semantics. The positive side effect here is that no cglib subclassing has to be applied at runtime, so there are no limitations in terms of class design. That is, the containing class may be final and so forth. In common scenarios, at bean methods are to be declared within at configuration classes, ensuring that full mode is always used and that cross method differences therefore get redirected to the container's lifecycle management. This prevents the same at bean method from accidentally being invoked through a regular Java call, which helps to reduce subtle bugs that can be hard to track down when operation in light mode. At bean and at configuration annotations are this you can see there. Here we are considering building a container programmatically by using register class question mark and in instantiation the Spring container by using annotation config application context. The following example shows how to do so. The class annotation config application context, a standalone application context accepting component classes as input, in particular at configuration annotated classes, but also plain at component types and JSR 330 compliant classes using Java x.inject annotations. This is in the package org.springframework.context.annotation. You can instantiate an annotation config application context by using no arg constructor and then configure it by using register method. This approach is particularly useful when programmatically building an application building an annotation configuring config application context. The following example shows how to do so. As an example 10, we are considering using at profile in environment abstraction in bean definition profiles. At profile can also be declared at method level to include one particular bean of a configuration class. For example, and for alternative variants of the particular beans, as following example shows. Annotation type profile indicates that the component is eligible for registration when one or more specified profiles are active. This in the package org.spring framework.context.annotation. At profile annotation lets you to indicate the component is eligible for registration when one or more specified profiles are active. Profile string may contain a simple profile name, for example, production, or a profile expression. A profile expression allows for more complicated profile logic to be expressed, for example, production and US East. Following operations are supplied in profile expressions. Bank sign, a logical not of the profile, ampersand, a logical and of the profile, and logical O of the profiles. You cannot mix the ampersand and O operators and O operators without using parentheses. For example, production and US East or EU Central is not a valid expression, must be expressed as production and open parentheses US East or US Central closing parentheses. You can use at profile as a meta annotation for the purpose of creating custom composed annotation. If a configuration class is marked with at profile, all of the bean methods and at import annotation associated with that class are bypassed unless one or more of the specified profiles are active. If at component and at configuration class is marked with at profile, open curly brace P1, P2 close curly brace, that class is not registered or processed unless the profile P1 and or P2 have been activated. If a given profile is prefixed with the not operator, the annotated element is registered only if the profile is not active. For example, given at profile P1 and not P2, registration will occur if the P1 is active and if the profile P2 is not active. Profile can be declared, can also be declared at the method level to include only one particular bean of a configuration class. For example, for alternative variants of a particular bean, as following example shows. The standalone data source method is available only in the development profile. JNDA data source method is available only in the production profile. With at profile on at bean methods, a special scenario may apply. In case of overloaded at bean methods of the same Java method name analogous to constructor overloading, the at profile condition needs to be consistently declared on all overloaded methods. If the conditions are inconsistent, only the condition on the first declaration among the overloaded methods matters. Therefore, at profile cannot be used on a select the overloaded method with a particular argument signature over another. Resolution between all factory methods for the same bean follows Spring's constructor resolution algorithm at creation time. If you want to define alternative bean with different profile conditions, use distinct Java method names that point to the uh, uh, same bean name by using @bean name attribute as shown in this example. If the argument signatures are all same, for example, variants have no argfactory methods, this is the only way to represent such arrangement with a valid Java class in the first place, since there can only be one method of a particular name and argument signature. XML bean definition profiles. It is also possible to avoid that the split and nest beans. In the XML counterpart is the profile attributes of the beans element. Our proceeding sample configuration can be rewritten in two XML files as follows. The XML counterpart does not support the profile expressions. It is possible to, however, to negate a profile by using the not operator. It is also possible to apply logical and by nesting the profiles. As an example 11, we are considering registering load time weaver. To enable load time weaving, you can add enable load time weaving to one of your configuration classes, as following example shows. Annotation type enable load time weaving activates Spring load time weaver for this application context, available as a bean with the name load time weaver, similar to the context colon load time weaver element in Spring XML. This is in the package org.springframework.context.annotation. Load time weaver is used by Spring to dynamically transform classes as they are loaded into the Java virtual machine JVM. To enable load time weaving, you can use @enable load time weaving to one of your configuration classes, as the following example shows. Alternatively, for XML configuration, you can use the context colon load time weaver element. Once configured for the application context, any bean within that application context may implement load time weaver aware, thereby receiving the reference to load time weaver instance. This is particularly useful in combination with Spring's JPA support, where load time weaving may be necessary for JPA class transformation. As an example 12, we are considering internationalization using message source in additional capabilities of application context. The following example shows resource bundle message source. The class resource bundle message source implementation that accesses resource bundles using specified base names. This class relies on the underlying JDK resource bundle implementation in combination with JDK's standard message passing provided by message format. This is in the package overflowed spring framework.context.support. The application context interface extends the interface called message source and therefore provide the internationalization I18N functionality. Spring also provide the hierarchical message source interface which can resolve messages hierarchically. Together, these interfaces provide the foundation upon which Spring affect message resolution. The method defined in these interfaces include string get message, string code, object array args, string default, local lock. The basic method used to retrieve a message from message source when no message is found for the specified local, the default message is used. Any arguments passed in become replacement values using message format functionality powered by the standard library. The string get message, string code, object args, local lock, essentially the same as the previous method, but one difference: no default message can be specified. If the message cannot be found, no such message exception is thrown. The string get message source resolvable local. All properties are used in preceding methods are also wrapped in the class named message source resolvable, which you can use with this method. When application context is loaded, it automatically searches for a message source being defined in the context. The bean must have a name message source. Bean defined in the context. Bean must have a name message source. If such a bean is found, it all calls the preceding method and delegated to the message source. If no method is found, application context attempts to find a parent containing bean with the same name. If does, it uses the bean as the message source. If the application context cannot find any source for the message, an empty delegating message source is instantiated in order to able to accept calls to the methods defined above. Spring provide message source implementations. Resource bundle message source, reloadable resource bundle message source, and static message source. All of the implement hierarchical message source in order to do nested messaging. All of them implement hierarchical message source in order to do nested messaging. The static message source is rarely used but provides programmatic ways to add messages to the source. Following example shows this one resource bundle message source. The example assumes that you have three resource bundles called format, exceptions and windows defined in your class path. Any request to resolve message is handled by the JDK standard way of resolving messages through resource bundle objects. For the purpose of the example, assume the content of two of the above resource bundle files as follows. The next example here shows the program to run the message source functionality. Remember that all application context implementations are also message source implementations, so that can be cast to the message source interface. Resulting output from this program is as follows. To summarize, the message source is defined in the file called beans.xml, which exists at the root of your class path. Message source bean definition refers to a number of resource bundles through the base names property. 3 files that are passed to the list of the base names property exist as files at the root of your class path are called format.properties, exception.properties, and windows.properties respectively. As an example 13, we are considering standard and custom events. The following example shows simple class that extend application event base class. The class application event class to be extended by all application events abstract, as it doesn't make sense for generic events to be published directly. This is in the package org.spring framework.context. Event handling in the application context is provided through application event class and the application listener interface. If a bean that implements application listener interface is deployed into the context, every time the application event get published to the application context, that bean is notified. Essentially, this is an standard observer design pattern. As of Stream 4.2, the event infrastructure has been significantly improved and offers an annotator-based model as well as ability to publish any arbitrary element, that is an object that does not necessarily extend the application event. When such an object is published, we wrap it in an event for you. You can create and publish your own custom events. Following example shows a simple class that extends Spring application event base class. To publish a custom application event, call the publish event method on the application event publisher. Typically, this is done by creating a class that implements application event publisher aware and registering it as a Spring Bean. Following example shows such a class. At configuration time, Spring container detects the email service. Implements application event publisher aware and automatically calls the set application event publisher. In reality, the parameter passed in the Spring's container itself, you are interacting with the application context through application event publisher interface. Accessor and other methods. And send email. To receive the custom application event, you create a class that implements application listener and register it as a Spring Bean. The following example shows such a class. Notice that application listener is generically parameterized with the type of your custom event, block list event. In this example, this means that on application event method can remain type safe, avoiding any need for downcasting. You can register as many event listeners as you wish, but not that by default event listeners receive event synchronously. This means that the publish event method blocks until all listeners have finished processing the event. One advantage of this synchronous and single-threaded approach is that when a listener receives an event, it operates inside the transaction context of a publisher if a transaction context is available. If another strategy for event publication becomes necessary, see the information in Spring application event multicast interface and simple application event multicast implementation for configuration options. Notify appropriate parties via notification address. The following example shows the bean definitions used to register and configure each of the classes we mentioned. Putting all it together, when send email method of the email service bean is called, there are any email messages that should be blocked. A custom event of the block list event is published. The block list notifier bean is registered as application listener and receive the block list event, at which point it can notify appropriate parties. Spring's event mechanism is designed for simple communication between Spring beans within the same application context. However, more sophisticated enterprise integration needs The separately maintained Spring integration project provides complete support for building lightweight, pattern-oriented, event-driven architectures that build upon the well-known Spring programming model. In example 14, we are considering annotation-based event listeners. You can register an event listener on any method of manage bean by using @event listener annotation. The block list notifier can be written as follows here. The annotation type event listener annotation that marks a method as a listener for application events. This is in the package org.springframework.context.event. The method signature once again declared the event type to which it listened, but this time with a flexible name and without implementing specific listener interface. The event type can also be narrowed through generics as long as the actual event type resolve your generic parameter as its implementation hierarchy. If your method should listen to several events, or if you want to define it with no parameter at all, the event types can also be specified on annotation itself. Notify appropriate parties via notification address. As an example 15, we are considering convenient access to low-level resources. Here you can configure a bean deployed into application context to implement the special callback interface resource loader aware to be automatically called back at the initialization time with the application context itself passed in as a resource loader. The interface resource loader aware interface to be implemented by any object that wishes to be notified of the resource loader, typically application context that it returns in. This is the alternative to an full application context dependency via the application context aware interface. This is in the package org.springframework.context. The optional usage of understanding of application context, you should familiarize yourself with the Spring resource abstraction as the application context is a resource loader which can be used to load resource objects. The resource is essentially more feature-rich version of JDK Java.NET URL class. In fact, implementation of resource wrap and instance of Java.NET URL where appropriate. A resource can obtain low-level resources from almost any location in a transparent fashion, including from the class path and a file system location anywhere describable with standard URL and other variations. If the resource location string is a simple path without any special prefixes, where those resources come from is specific and appropriate to actual application context type. You can configure a bean deployed into the application context to implement a special callback interface resource loader aware to be automatically called back at initialization time with the appropriate application itself passed in as a resource loader. You can also expose properties of a resource to be used to access static resources. They are injected into it like any other properties. You can specify those resource properties as simple string path and rely on automatic conversion from those text strings to actual resource objects when the bean is deployed. The location path or paths applied to application context constructor are actually resource strings and in simple form are treated appropriately according to the specific context implementation. For example, class path XML application context treats a simple location path as a class path location. You can also use location path resource strings with special prefixes to force loading of definition from the class path or URL regardless of the actual context type. Application startup tracking. Here's an example of instrumentation in annotation in the annotation config application context. The class annotation config application context is standalone application context accepting a component classes as input, in particular at configuration annotated classes, but also plain at component types and JSR 330 compliant classes using Java x.inject.annotations. Spring this in the package org.spring spring framework.context.annotation. The application context manages the lifecycle of Spring application and provides rich application model around the components. As a result, complex application can have equally complex component graphs and startup phases. Tracking the application startup steps with specific metrics can help to understand where time is being spent during the startup phase, but it can also be used as a way to better understand the context lifecycle as a whole. The abstract application context and its subclasses is instrumented with application startup, which collects the startup step data about various startup phases, application context life cycle, base packages scanning, config management, beans life cycle, instantiation, smart initialization, post processing, application event processing. Here's an example of instrumentation annotation config application context. The application context is already instrumented with multiple steps. Once recorded, these startup steps can be collected, displayed, and analyzed with the specific tools. The default application startup implementation is no op variant for minimal overhead. This means no metrics will be collected during application startup by default. Spring framework ships with an implementation for tracking startup steps with Java flight recorder. Flight recorder application startup. To use this variant, you must configure instance of it to the application context as soon as it's been created. Developers can also use application startup infrastructure if they are providing with their own abstract application context subclasses if they wish to collect more precise data. Application startup means is meant to be only used during application startup and for core container. This is by no means a replacement for Java profilers or matrix libraries like Micrometer. To start collecting custom startup step, components can either get application startup instance from the application context directory, make their component implement application startup aware, or ask for application startup type on any injection point. Developers should not use the Spring.asterisk namespace when creating custom startup steps. This namespace is reserved for internal Spring usage and is subject to change. Here, create a startup step and start recording. Add tagging information to to the current step. Perform actual pace via instrumenting. End the current step. As an example 17, we are considering convenient application context instantiation for web applications. You can register an application context by using the context loader listener, as the following example shows. The class context loader listener bootstrap listener to start up and shut down Spring's root web application context simply delegates to context loader as well as to context cleanup listener. This is in the package org.springframework.web.context. You can create application context instances declaratively by using, for example, context loader. Of course, you can also create application context instances programmatically by using one of the application context implementations. You can register an application context by using application context listener, as the following example shows. The listener inspects the context configuration parameter. If the parameter does not exist, the listener uses /web-inf/application context.xml as a default. When the parameter does exist, listener separates the string by using predefined delimiters, comma, semicolon, and white space, and uses the values as locations where application contexts are searched. Any anti-style pattern path patterns are supported as well. Examples are /web-inf/context.xml for all files with names that ends with context.xml and reside in the web-inf directory, and the /web-inf/***context.xml for all such files in any subdirectory of web-inf. As an example 18, we are considering deploying a Spring application context as a Java EE raw file. For simple deployment of a Spring application context as a Java EE raw file, step 1, package all application classes into a raw file, area file, which is a standard Java file with a different file extension. Step 2, add all required library jars into the root of the area file. Step 3, add the meta inf/array.xml deployment descriptor as shown in the Java doc for Spring context resource adapter and the corresponding Spring XML bean definition files, typically meta inf/spring context XML. Step 4, drop the resulting RAR file into your application server's deployment directory. It is possible to deploy a Spring application context as a raw file, encapsulating the context and all its required bean classes and the libraries jar in the Jakarta EE raw deployment unit. This is equivalent of bootstrapping a standalone application context only hosted in the Jakarta EE environment, being able to access the Jakarta EE service facilities. RAR deployment is more natural alternative to a scenario of deployment of headless WAR file. In effect, a WAR file without any HTTP entry points that is used only for bootstrapping a Spring application context in a Jakarta EE environment. RAR deployment is ideal for application contexts that do not need HTTP entry points but rather consist only of message endpoint and scheduled jobs. Beans in such context can use application server resources such as JTA transaction manager and JNDI bound JDBC data source instances and JMS connection factory instances, and also register with platforms JMX server, all through Spring's standard transaction management and JNDI and JMX support facilities. Application components can also interact with the application server's JCA work manager through Spring's task execution abstraction. Such raw deployment units are usually self-contained. They do not expose a components to the outside world, not even to other modules of the same application. Interaction with RAR-based application context usually occurred through JMS destination that it shared with other modules. RAR-based application context may also, for example, schedule some jobs to react to new files in the file system or the like. If it does not allow synchronous access to from the outside, it could, for example, export RAMI endpoint, which may be used by other application modules on the same machine. As an error example, we can consider class application context exception thrown during application context initialization. This is in the package org.stringframework.context. As an error example, we can consider unable to start servlet web server application context due to missing servlet web server application servlet web server factory bean. Now we are focusing on SpEL. The Spring expression module provides a powerful expression language for querying and manipulating an object graph at runtime. It is an extension of the unified expression language, unified EL, as I specified in the JSP 2.1 specification. The language supports settings and gettings, property values, property assignment, method invocation, accessing the content of arrays, collections and indexes, logical and arithmetic operators, named variables, and retrieval of objects by name from Spring's IOC container. It also supports list projection and selection as well as common list aggregations. Here you can see a Spring expression language, SpEL API, and an example. The SpEL API has many interfaces and classes which are defined as follows: expression interface, SpEL expression, SpEL expression class, expression parser interface, SpEL expression parser class, evaluation context interface, standard evaluation context, here interface expression parser passes expression strings into compiled expressions that can be evaluated, supports parsing templates as well as standard expression strings. Here SpEL expression parser class, SpEL parser instances are reusable and thread safe. Interface expression, an expression capable of evaluating itself against the context objects, encapsulates the details of a previously passed expression string, provides a common abstraction for expression evaluation. Class SpEL expression. SpEL expression represents a past valid expression that is ready to be evaluated in a specified context. An expression can be evaluated standalone or in a specified context. During expression evaluation, the context may be asked to resolve the references to types, beans, properties, and methods. Interface evaluation context. Expressions are executed in an evaluation context. It is in this context that references are resolved when encountered during expression evaluation. Class standard evaluation context. A powerful and highly configurable evaluation context implementation. This context uses standard implementation of all applicable strategies based on the on reflection to resolve properties, methods, and fields. Here you can see expression parser, and here you can see SpEL expression parser. An expression parser is connected to expression. Parse expression is passed from expression parser to expression, and Spring this is a Spring expression string, and this is this is expression, and this SpEL expression. Expression is connected to expression interacts with evaluation context, and standard. This is a standard evaluation context here, and expression produces get value. Expression passes get value here. As an example, we can consider this Maven segment. This is here you can see artifact ID, expression, Spring expression language, SpEL, powerful expression language for querying and manipulating an object graph at runtime. It is an extension of the unified expression language, unified EL, as specified in the JSP 2.1 specification. This is in the group ID org.spring framework. As an example too, we can consider package org.spring framework.expression, co-abstractions behind the Spring expression language. Here we are considering evaluation. The following code introduces SpEL API to evaluate literal string expression hello world. Interface expression, an expression capable of evaluating itself against context objects, encapsulates the details of previously passed expression string, provide the common abstraction for expression evaluation. This is in the package org.spring framework.expression. Here the value of the message variable is hello world. SpEL classes and interfaces you are most likely use are located in org.spring framework.expression package, and its subpackages such as SpEL.support. The expression parser interface is responsible for passing an expression string. In this example, the expression string is a literal denoted by surrounding single quotation marks. The expression interface is responsible for evaluating previously defined expression string. Two exceptions that can be thrown: past exception and evaluation exception. When calling parser.past exception and exp.getValue respectively. Here we are considering parser configuration. Following example demonstrate how to automatically grow a list. The SpEL parser configuration object for SpEL expression parser. This is in the package org.spring framework.expression.spel. It is possible to configure SpEL expression parser by using parser configuration object org.spring framework.expression.spel.spell parser configuration, The configuration object controls the behavior of some expression components. For example, if you index into an array or collection and the element of that specified index is null, SpEL can automatically create the element. This is useful when using expressions made up of chain of property references. If you index into an array or a list and specify an index that is beyond the end of the current size of the array or list, SpEL can automatically grow the array or list to accommodate that index. In order to add an element at a specified index, SpEL will try to create the element using the element type's default constructor before setting the specified value. If the element type does not have the default constructor, null will be added to the array or list. If there is no built-in or custom converter that knows how to set the value, null will remain in the array or list in the specified index. Following example demonstrate how automatically grow a list. Turn on auto null reference initialization, auto collection growing. Demo.list will now be a real collection of 4 elements. Each entry is a new empty string. Here we are considering compiler configuration. After selecting a mod, use the SpEL parser configuration to configure the parser. The following example shows how to do it. The enum SpEL compiler mod captures the possible configuration settings for a compiler that can be used when evaluating expressions. This is in the package org.springframework.expression.spel. The compiler is not turned on by default, but you can turn it on either of two different ways. You can turn it on by using parser configuration process, or by using Spring property when SpEL usage is embedded inside another component. So we are going to discuss both options. The compiler can operate in one of 3 modes, which is captured in the org.springframework.expression.spel compiler mode enum. The modes are as follows: off, default, the compiler is switched off; immediate, and immediate mode. In immediate mode, expressions are compiled as soon as possible. This is typically after the first interpreted evaluation. If the compiled expression fails, typically due to type changing, as a caller of the expression evaluation receives an exception. Mixed. In mixed mode, the expression silently switch between interpreted and compiled mode over time. After some number of interpreted runs, they switch to compile form, and if something goes wrong in the compiled form, such as a type changing, the expression automatically switch back to the interpreted form again. Sometimes later it may generate another compiled form, and switch to it. Basically, the exception that the user gets in immediate modes is instead handled internally. Immediate mode exists because mixed mode could cause issues for expressions that have side effects. If a compiled expression blows up after partially succeeding, it may have already done something that has affected the state of the system. If this happens, the caller may not want it to silently rerun the interpreted mode, since part of the expression may be running twice. After selecting a mod, use the SpEL parser configuration to configure the parser. Following example shows how to do so. When you specify a compiler mode, you can also specify a class loader. Passing null is allowed. Compiled expressions are defined in a child class loader created under any that is supported that is supplied. It is important to ensure that if the class load is specified, it can see all type of involved expression evaluation process. If you do not specify a class loader, the default class loader is used. Typically, context class loader for the thread that is running during the expression evaluation. Second way to configure the compile is for use the when SpEL is embedded inside some other component, and it may not be possible to configure it through a configuration object. In these cases, it is possible to set the spring.expression.compile.mod property via a JVM system property, or via the Spring properties mechanism to one of the SpEL compiler mod enums values of immediate or mixed. Now we are considering XML configurations in expressions in bean definitions. The property or construct argument value can be set by using expressions, as following example shows. Other properties. The following example shows how to access to the system properties bean as a SpEL variable. All bean in the application context are available as predefined variables with their common bean names. This includes the standard context beans such as environment of type org.spring framework.code env.environment, as well as system properties and system environment of type map string object for access to the runtime environment. Following example shows access to the system properties bean as a SpEL variable. Note that you do not have to prefix the predefined variables with the hash symbol here. Other properties. Here we are considering annotation configuration. The following example sets the default value of the field. To specify a default value, you can place at value annotation on fields methods and method or constructor parameters. The following example sets the default value of the field. Here we are considering literal expressions in language reference. Typically they are not used in isolation like this, but rather as a part of more complex expression, for example using a literal on side of a logical comparison operator. The method public expression, pass expression string, expression string, pass the expression string and return an expression object. You can use for repeated evaluation. This is in the package. This is in the class template aware expression parser, and in the package org.springframework.expression.common. The types of literal expression supported are strings, numerical values, int, int, real, hex, boolean, and null. Strings are delimited by using single quotation marks. To put a single quotation mark itself in a string, use two single quotation mark characters. The following listing shows simple usage of literals. Typically they are not used in isolation like this, but rather as a part of more complex expression, for example using a literal in one side of a logical comparison operator. Numbers support the use of negative sign, exponential notations, and decimal points. By default real numbers are passed by using pass double dot pass double. Evals to hello world. Evals to 214743834647. As an exception example, we can consider SpEL evaluation exception. The class SpEL evaluation exception, root exception for Spring EL related exceptions. Rather than holding a hard-coded string indicating the problem, it records the message key and the inserts for the message. See SpEL message for the list of all possible messages that can occur in the documentation, and this is in the package org.springframework.expression.spel. As an example, we can consider this. Here you can see a fail to instantiate compile expression in org.springframework.expression.spel .spel.standard.spel SPL compile, and here caused by Java-Lang verifier, etc. And here you can see again org.springframework.expression.spel.standard.spel compile, etc. Now we are focusing on test. The Spring test module supports the unit testing and integration testing of Spring components with JUnit or TestNG. It provides consistent loading of Spring application context and caching of those contexts. It also provides mock object that you can use to test your code in isolation. As an example, we can consider this Maven segment. You can see here the artifact ID spring-test, Spring test context framework. Spring test supports the unit testing and integration testing of Spring component with JUnit or TestNG. It provides consistent loading and caching of Spring application context and provides mock objects that you can use to test your code in isolation. This is in the group ID org.spring framework. As an example 2, we can consider package org.springframework.mock. Now we are focusing on integration testing. This library includes the the jar file in the with related to a spring-test library includes the org.springframework.test package, which contains valuable classes for integration testing with the Spring container. This testing does not rely on an application server or other deployment environment. Such tests are slower to run than unit tests, but much faster than the equivalent Selenium test or remote test that rely on deployment to an application server. This is in the this is a package org.springframework.test. With regarding unit test, mock objects in unit test related to the environment, the org.springframework.mock.env package contains mock implementation of environment and property source abstractions. Mock environment and mock property source are useful for developing out-of-container test for code that depends on environment specific properties. This is package org.springframework.mock.env. This package contains mock implementation of the environment and property source abstraction introduced in Spring 3.1. Now we are focusing on general testing utilities in unit testing support classes. The org.springframework.test.util package contains several general purpose utilities for use in unit and integration testing. The package org.springframework.test.util general utility classes for use in unit and integration tests. AOP test utils is a collection of AOP related utility methods. You can use these methods to obtain a reference to the underlying target object hidden behind one or more Spring proxies. For example, if you have configured a bean as a dynamic mock by using a library such as EasyMock or Mockito, and the mock is wrapped in a Spring proxy, you may need direct access to the underlying mock to configure expectations on it and perform verifications. Reflection test utils is a collection of reflection-based utility methods. You can use these methods in testing scenarios where you need to change the value of a constant, set an unpublic field, invoke an unpublic setter method, or invoke an unpublic configuration or lifecycle callback method when testing application code for use cases such as following: ORM frameworks such as JPA and Hibernate that condone private or protected field access as opposed to public setter methods for properties in a domain entity. Spring support for annotations such as autoavoid, at inject, and at resource that provide dependency injection for private or protected fields, setter methods, and configuration methods. Use of annotations such as at post construct, at destroy, and pre-destroy for lifecycle callbacks method. Test socket utils is a simple utility for finding available TCP ports on localhost for use in integration testing scenarios. Test socket utils can be used in integration test which start an external server on available random port. However, these utilities make no guarantee about subsequent availability of a given port and are therefore unreliable. Instead of using test socket utils to find an available local port for a server, it is recommended that you rely on a server ability to start a random ephemeral port that it select or is assigned by operation system by the operating system. To interact with that server, you should query the server for the port it is currently using. Here we are considering context configuration with XML resources in context management in goals of integrating testing. The path that represent the resource URL, that is the path prefix with the class path, file, HTTP, etc. is used as is. The annotation type context configuration. At context configuration defines a class level metadata that is used to determine how to load and configure an application context for integration testing. This is in the package org.springframework.test.context. The to load an application context for your tests by using XML configuration file, annotate your test class with context configuration and configure the locations attributes with an array that contain the resource locations of XML configuration data. A plain or relative path, for example, context.xml is treated as a class path resource that is relative to the package in which the test class is defined. A path starting with / is treated as an absolute path, absolute class path location, for example, /org. /example /config.xml. A path that represents a resource, that is a path prefix with class path, file, HTTP, etc. is used as is. Here you can see setting locations attribute to a list of XML files. Application context will be loaded from /app-config.xml and test-config.xml in the root of the class path. This is my class body. Here we are considering JDBC testing support. The org.springframework.test.jdbc package contains JDBC test utils, which is a collection of JDBC related utility functions intended to simplify standard database testing scenarios. Class JDBC test utils. JDBC test utils is a collection of JDBC related utility functions intended to simplify standard database testing scenarios. This is in the package org.springframework.test.jdbc. Especially JDBC test utils provide following static utility methods. Count rows in table counts the number of rows in a given table. Count rows in table where counts the number of rows in the given table by using the provided where clause. Delete from tables. Delete all rows from the specified table. Delete from table where. Delete the rows from a given table by using the provided where clause. Drop tables. Drops the table drops the specified tables. Abstract transactional JUnit for Spring context test and abstract transactional JUnit transactional test ng Spring context test provide convenience method that delegate to aforementioned methods in JDBC test utils. The Spring JDBC module provides support for configuring and launching an embedded database, which you can use in integration tests that interact with the database. Now we are considering Spring testing annotations. In annotations, the following example shows how to use the @web app configuration annotation. Annotation type web app configuration. @web app configuration is a class level annotation that is used to declare that the application context loaded for an integration test should be an web application context. This is in the package org.springframework.test.context.web. Web application configuration is a class level annotation that you can use to declare that the application context loaded for an integration test should be a web application context. The mere presence of web application configuration on a test class ensures that the web application context is loaded for test using the default value of file src/main/web app for the class path to root of the web application, that is the resource based path. The resource based path is used behind the scenes to create mock servlet context, which serves as a servlet context for the test web application context. Here you can see the web application context, web application configuration annotation, class body here. Metadata annotation support for testing. For example, if we wish to create a composed annotation that combines the @test and @tag annotations from JUnit Jupyter with a transactional annotation from Spring, we could create a transactional integration test annotation as follows. We can use our custom transactional dev test config. This is a custom created one. Since the JUnit Jupyter supports the use of @test, repeated test and parameterized test and others as metadata annotations, you can also create custom compose annotation at the test method level. For example, if you wish to create compose annotation that combines @test and tag annotations from JUnit Jupyter with the transactional annotation from Spring, we could create a transactional integration test annotation as follows. Then we can use our custom transactional integration test annotation to simplify the configuration of individual JUnit Jupyter based test method as follows. org.junit.jupyter.api.tag, org.junit.jupyter.api.test. Here we are considering merging test execution listeners into implementations in Spring Test Context Framework. Following listing demonstrate this style of configuration. Annotation type test execution listeners. Test execution listeners define class level metadata for configuring which test execution listener should be registered with text context manager. This is in the package org.springframework.test.context. If a custom test execution listener is registered via @test execution listeners, the default listeners are not registered. In most common testing scenarios, this effectively forces the developer to manually declare all default listeners in addition to any other custom listeners. The following listing demonstrate this style of configuration. The challenge with this approach is that it required that developer know exactly which listeners are registered by default. Moreover, the set of default listeners can change from release to release. For example, SQL script execution listener was introduced in Spring Framework 4.1 and dirty's context before mods dirty's context before mods test execution listener was introduced in Spring Framework 4.2. Furthermore, third-party frameworks like Spring Boot and Spring Security register their own default test execution listener implementation by using aforementioned automatic discovery mechanisms. A class body here. Here we are considering bind to controller in setup in web test client. For WebFlux applications, use the following, which loads the infrastructure equivalent to the WebFlux Java config, registers the given controllers and create the web handler chain to handle requests. Interface web test client for testing web servers that uses web client internally to perform requests while also providing a fluent API to verify responses. This client can connect to any server over HTTP or to a WebFlux application via mock request and response objects. This is the package org.springframework.test.web.reactive.server. These setups allows you to test specific controllers via mock request and response object without running a server. For WebFlux applications, use the following, which loads infrastructure equivalent to the WebFlux Java config, registers a given controller and create a web handler chain to handle requests. Now we are in example 12, we are considering writing tests to assert the response status and headers. Use following. The method status asserts expect status, assertions on the response status. The method header assertions expect header assertions on the headers of the response. These are in interface web test client dot response spec in the package org.springframework.test.web.reactives.server. The test web client provides an API identical to web client up to the point of performing the request by using exchange method. After call to the exchange, web test client diverges from the web client and instead continues with the workflow to verify responses to assert the response status and headers. Use following. Here we are considering setup choices in the mock MVC. Here you can inject the mock service into the test to test up and verify your expectations. As following example shows, the class mock MVC main entry point for server-side Spring MVC test support. This is in the package org.springframework.test.web.servlet. Mock MVC can be set up in one of two ways. One is to point directly to the controller you want to test, programmatically configure the Spring MVC infrastructure. The second is to point to the Spring configuration with the Spring MVC and controller infrastructure with it. To set up mock MVC for testing a specific controller, use following, or you can also use this setup when testing through web test client, which delegates the same builder as shown here. To set up a mock MVC through Spring configuration, use following here. Or you can use this setup when testing through web test client which delegates the same builder as shown here. Which setup option should you use? The Spring Web App Context Setup loads your actual Spring MVC configuration, resulting in a more complete integration test, since the test context framework catches the loaded Spring configuration. It helps keep test running fast even as you introduce more tests in your test shoot. Furthermore, you can inject mock services into the controllers through Spring configuration to remain focused on testing the web layer. Following example declares a mock service with Mockito. You can inject mock service into the test to set up and verify your expectation, as following example shows. The standalone setup, on the other hand, is a little closer to a unit test. It tests one controller at a time. You can manually inject the controller with the mock dependencies, and it does not involve the loading Spring configuration. Such tests are more focused on style and make it easier to see which controller is being tested, whether any specific Spring MVC configuration is required to work, and so on. The standalone setup is also a very convenient way to write ad hoc tests to verify specific behavior or to debug an issue. As with most integration versus unit testing debates, there is no right or wrong answer. However, using the standalone setup does imply the need for additional web app context setup test in order to verify your Spring MVC configuration. Alternatively, you can write all your tests with web application context setup in order to always test against your actual Spring MVC configuration. As an example 14, we are considering testing client applications. The idea is to declare expected requests and to provide stub responses so that you can focus on testing code in isolation, that is without running a server. The following example shows how to do so. The class mock REST service server. The main entry point for the client side REST testing, used for test that involve direct or indirect use of REST template, provides a way to set up expected requests that will be performed through the REST template, as well as mock responses to send back, thus removing the need for an actual server. This in the package is org.springframework.test.web.client. You can use client-side test to test code that internally uses REST template. The idea is to declare expected request and to provide stub responses so that you can focus on testing the code in isolation, that is without running a server. Following example shows how to do so. In this example, mock REST service server, the central class for client-side REST test, configures the REST template with a custom client HTTP request factory that asserts actual request against expectation and return stub responses. in this case, we expect expect a request to / greeting and want to return a 200 response with text plain content. We can define additional expected requests and stub responses. The REST template can be used in the client-side code as well. At the end of testing, mockserver.verify can be used to verify that all expectations have been satisfied. Test code that uses the above REST template. As an exception example, we can use illegal example. We are considering illegal state exception. This can be occurred in the method application context. This is if an error occurs while retrieving the application context in the application context.get application context method. This method is in the interface test context and in the package org.springframework.test.context. As an error example, we can consider this one: mock HTTP servlet response status 200 and error message equal null and etc. This is end of my presentation. Thank you for watching it.